Hello students, welcome to Soras's classes. This video is Way ANOVA part 3. Now we will begin this video from where we have ended in the previous video. So from the previous video we found out that the total sum of square, that is TSS, this is equals to sum of squares due to factor A, that is SSA, plus sum of squares due to factor B or SSB, plus sum of squares due to error, which is written as SSE. Now, under the assumption of normality of errors, under the assumption of normality of error, we can say that SSA by sigma square, SSB by sigma square, and SSE by sigma square, these three are independently distributed chi-square random variables. So they are independent and they follow chi-square distribution, that is they are chi-square random variables with degrees of freedom as k minus 1, L minus 1, k minus 1, L minus 1, and k minus 1 into L minus 1 respectively. So SSA by sigma square, it follows chi-square distribution with degrees of freedom k minus 1. SSB by sigma square, it is also a chi-square random variable with degrees of freedom L minus 1, and SSE by sigma square, it is a chi-square random variables with degrees of freedom equals to k minus 1 into L minus 1. So SSA by sigma square has degrees of freedom as k minus 1, SSB by sigma square it has degrees of freedom L minus 1, and SSE by sigma square it has degrees of freedom k minus 1 into L minus 1. So this, if we add the sum of these degrees of freedom in the right hand side, we will get the degrees of freedom of left hand side. So we are having k minus 1 into L minus 1, k minus 1 plus L minus 1 plus KL minus K minus L plus 1. So from here we can say that this is the left hand side, this is the right hand side. So in the left hand side we will have KL minus 1. So the degrees of freedom of, in the right hand side it is equals to KL minus 1. Hence in the two-way analysis, where we are interested in the equality of effect of the factor of interest, that is factor A, so in two-way analysis where factor A is the factor of interest, we will have our H naught would be equals to mu1 is equals to mu2 is equals to so on till mu k, and the alternative, that is HA, it would be as mu1, mu I is not equals to mu j, it is for at least one pair of I comma j, where I runs from 1 to k and j it runs from 1 to L. So for at least one pair of ij, this mu I is not equals to mu j. Now since this mu I, this is equals to 1 by L summation j runs from 1 to L, mu plus tau I plus beta j. So this is equals to mu plus tau I plus 1 by L into summation j runs from 1 to L beta j. So this part is equals to 0. So mu I is equals to mu plus tau I. So mu I is equals to mu plus tau I. So from here we can equivalently write our H naught. This is equals to T1 is equals to T2 is equals to so on till Tk, which is equals to 0, and H alpha is that our Ti, this is not equals to 0 for at least 1 I, where I runs from 1 to k. So our H naught is that tau 1 plus tau is equals to tau 2 is equals to so on till tau k, which is equals to 0. And our alternative hypothesis is that at least for 1 I we would have our tau I not equals to 0. Now this test, the test we will be using is always a right-tailed test. Right-tailed test with the rejection region towards the right tail of F curve or F distribution curve. So with the rejection region towards the right tail of F distribution curve. So now we will draw the ANOVA table for two-way analysis. So this is the ANOVA table for two-way classified data. Now in the first column we have source of variation. So different source of variations are, number one is between the levels of factor A. So the first one is between the levels of factor A. Next is between the levels of factor B. Between the levels of factor B. Next is error. Next source of variation is error, and the final one is the total, that is the total source of variation. So the degrees of freedom corresponding to the factors of A, it would be k minus 1, and the degrees of freedom corresponding to the source of variation between the levels of factor B, it is equals to L minus 1. For error, it is the degrees of freedom is equals to k minus 1 into L minus 1, and the total degrees of freedom is equals to KL minus 1. Now the sum of squares. Now sum of squares corresponding to factor A, this is equals to SSA, which is equals to L into summation I runs from 1 to k yi naught cap minus y double naught cap whole square. So SSA is equals to this. Now sum of squares corresponding to factor B, it is SSB, which is equals to k into summation j runs from 1 to L y naught j bar minus y double naught bar whole square. Now sum of squares corresponding to error is sum of squares of error or SSE, which is equals to summation I runs from 1 to k, summation j runs from 1 to L, then yij minus yi naught bar minus y naught j bar plus y double naught bar whole square. So this is SSE, and total sum of squares, that is TSS, it is equals to summation I runs from 1 to k, summation j runs from 1 to l, yij minus y double naught bar whole square. So these are the sum of squares. Now mean square corresponding to factor A, that is MSA, this is equals to SSA minus its corresponding degrees of freedom, that is K minus 1. Similarly, MSB, this is equals to SSB divided by L minus 1. So MSA is equals to SSA divided by K minus 1. MSB is equals to SSB divided by L minus 1, which is the corresponding degrees of freedom. MSE is equals to, this is equals to SSE divided by the corresponding degrees of freedom, that is K minus 1 into L minus 1. So these are the three mean squares. So the f value observed, this is f naught, which is equals to MSA divided by MSE. Now here in f naught we have MSA divided by MSE because A was our factor, or that is A was our factor of interest. Since A was our factor of interest. Now if B was our factor of interest, then f naught would have been, so suppose B was our factor of interest, in that situation our f naught would have been MSB divided by MSE. So if B was our factor of interest, and if the experimenter have to see the effect of both the factors, then both of them would be here in the f observed, that is f naught A, which is equals to MSA divided by MSE, and f naught B, which is equals to MSB divided by MSE. So this is the observed value of f. Now what we would do is that this f, so this would be our observed value of f. Now our f naught A, it would follow the f distributions with degrees of freedom as k minus 1 and k minus 1 into L minus 1. So f naught A, it follows f distribution with degrees of freedom as k minus 1 and k minus 1 into L minus 1, and we reject h naught, and we reject, and this h naught is rejected, that is we reject h naught if our f naught A, that is the observed value of A, this is greater than f alpha with degrees of freedom k minus 1 and k minus 1 into L minus 1. Now here this alpha is the level of significance. This alpha is the level of significance. So if our f naught A, that is the observed value of f, it is greater than f alpha, that is the tabulated value of f, that is f alpha with degrees of freedom as k minus 1 and k minus 1 into L minus 1, then the h naught is rejected. Otherwise h naught cannot be rejected. So otherwise h naught cannot be rejected. Similarly, this f naught B, FOB, this follows f distribution with parameters L minus 1 and k minus 1 into L minus 1. So it follows the f distribution with parameters L minus 1 and product of k minus 1 and L minus 1. Now if this f naught b, this calculated value of f, if it is greater than f alpha L minus 1 comma k minus 1 into L minus 1, if this f naught b is greater than our tabulated value of f, then we reject the h naught, which is that beta 1 is equals to beta 2 is all equals to beta L, which is equals to 0. So we will reject this h naught against the alternative hypothesis, which is beta j is not equals to 0 for at least 1j, So if this f naught b, this is greater than f alpha comma L minus 1 comma k minus 1 into L minus 1 as degrees of freedom, then we reject our h naught. Otherwise our h naught will not be rejected. So this is the two-way analysis for testing the data which is affected by two factors.